Okay, let's begin. So, first off, some announcements. Test 2. I'm going to make that March 29th. So the last topic for the test, I should start it today. I should finish it by Tuesday. If I have a snow day, I'll finish it on Thursday, but then this is a week after that Thursday. So you should have enough time to prepare for that. Again, the review's already on the website, so make sure you go through it. For those of you who already spoke to me, you kind of know a better plan of action than what you did last time. And so, waiting on the rest of you. There were some of you I couldn't see today, but you can see me after my second class at 8 if you'll be around. I can spend a half an hour or so, or a little bit later. Tomorrow is also probably an option. If any of you can meet with me tomorrow, I can be here by 4:30ish. Because I teach until 4 somewhere else. And yeah, and then there's always next week. But that's, huh? Huh? In the math department. So yeah, so that's when the second test is going to be. So about a week and a half from today. Or a little bit, 2 weeks. 2 weeks and a half from today. And today I should start the last topic for that test, but we'll finish it up on Tuesday. Worst case scenario, Thursday. So that's that. So let's 13.6. So we're going to continue with 13.6. We really kind of slowed down here because the concept of a normal vector and all that stuff is very important. So I very slowly went over that over and over. Make sure you understand that. Let's continue. What can you tell me about a surface? Just to do a small review before we start. What's a surface?
A double integral?
No. No.
It's a 2D object.
It's a 2D object. So this is just a 2D object. What does that mean? It has 2 parameters if you're parameterizing it. Integrals are sums, so it wouldn't be that. And an area is just a measure of how much space a 2D object takes up. But a surface is a 2-dimensional object, which means it has 2 parameters if you're parameterizing it. Or it's if you can write it as a scalar function, it's a 2-variable function. Right, so it has to be something like z equals f of x, y. Right, there are 2 variables x and y, and the third variable represents the output. So that's what a surface is. Now we discussed something important, how to find the normal vector to a surface. So tell me about finding normals.
Crossproduct.
Be specific. Give me some situations and then a formula that would work in that situation.
You take the partial derivative of the given vector that is.
Okay, so you have one case. So given a surface has a vector function, let's say it's r. How would you describe it?
R u v.
R of u v. Right? Don't be married to those letters. It doesn't matter what letters you call it. But it's a vector function with 2 variables in it. Yeah. Then.
Partial with respect to u, cross product with partial with respect to v.
Right, so if you take r sub u, cross product with r sub v, that's one way to get a normal vector. In fact, that's the definition of how we can get a normal vector. Okay? And the direction in which this is going to be pointing will make a difference in the future, but it's just going to be like you're taking the positive or the negative of this, and we'll talk about situations where that comes into play. So given a parameterization, as this, you can find the normal vector by taking the cross product of the partials with respect to each variable. Give me another situation.
So if you have something like x square plus z square, and if you
What is x squared plus z squared?
if it is a equation of a cylinder or something equation
Yeah?
sort of
The surface is written in scalar form.
So given a scalar form, so you
so that
continue.
has been negative. So
For example, what would a scalar form look like? Give me an example of a scalar form.
Z equals f of xy.
Z equals f of xy. Okay. Now suppose we can write a function in that form. Tell me how we can find a normal vector to that function.
It would be the partial with respect to x, the partial with respect to y, and then negative 1.
So your n can be, if you plug this directly into that definition with a certain parameterization, technically you'll have negatives here, but that can change. And then positive 1. The important is these two guys should have a different sign than that guy. And again, depending on what direction you want that normal to point in, you might take the plus or minus of this answer. Okay. Now, the recommendation is always try to apply 2 unless it doesn't apply anymore, because it will always be easier to get away with this than to get away with that. In fact, we derive this formula by doing the cross product on a certain parameterization, right? So basically what we did was we went over here and we parameterized the vector in terms of x and y as the x is itself, the y is itself, and the z is f of x, y. And applying this formula and doing the cross product, this is what we ended up with. So this part starts you ahead of the game. It starts you after the cross product has been done. So it will take you less work to figure out the normal vector if you're in this situation. There are times when you're not in this situation and you have to go straight back to the definition. Okay, but this part, the second way is actually you applying the definition, and so you can start a little bit ahead, cut down some of the computation time. Okay. Can you tell me, briefly speaking, some situations where problem 2 might not work? What kind of situation can you be in?
For example, if you have a surface where you need to find, you have the surface containing the top part and the bottom part.
Mm-hmm.
So for it would be equation of a cylinder.
Oh, that doesn't really have a top and a bottom part, really. But okay, so let's say you have a cylinder pointing like that. Okay. Why would this be a problem?
So if you want to do the second one, you need to do 2 times. So for example, you are not given parameter z is greater than 0 or something.
Okay. But a normal vector to this would actually have z component 0. Right? And that's why this formula could never work.
So this formula
Right,
would
so-
not work in equation of a sphere probably.
Yeah, but that's a different situation other than what you just described. Right? The reason why a cylinder wouldn't work is because your z component is just, it's not the right number. It has to be a 0 here.
0.
A sphere is a different consideration. Although last time I told you about the radial vector, which always works, but yes, the sphere would have a different formula if you're on top of the sphere versus the bottom. So the top part of the sphere, the normal vector would have a +1 in this component, while at the bottom part of the sphere, it would have the -1 in this component. And so you'll have to split the formula into 2 if you're using this formula. So there are those sort of considerations. Okay, now given that, tell me how to find the area of a surface S over a region D. Meaning, here you are in some space, you have some surface doing its thing, you can project it over some region. For example here, it's in the XY plane, doesn't have to be. But just as an idea, this is your surface. How can I find its area? The part of the area of the surface that's restricted to being projected above this region.
We would find the normal vector first,
Area is going to be the double integral over D,
and then magnitude of the normal vector.
magnitude of the normal vector.
and then dx.
By the way, you should always remember when you see a normal vector, there are one of two ways to find it, and depending on the situation I'm in, that's the formula that I'm going to put in here. Right? So that's how you'd find the area. So that kind of covers the concepts that we've covered so far. We've done some examples of some different kinds of surfaces, but these were the main ideas that you need to be aware of. Right? They're going to be very important when we're setting up surface integrals, which hopefully I'll get to start today. But these are concepts that you'll need to understand in order to even start those. Okay. Let's just do a few examples here. Yeah, I'm just going to do a couple of area examples and then we move on to surface integrals. So test 2, March 29th. Okay, areas we found them in Calc 3. I tested you on that on test 1. So for now, we're kind of going to do area problems that you'd sort of employ the 392 way of doing it. So we're going to find areas if we're given a parameterization. So example. Find the area of the surface given by, so here I'm giving you a parameterization for the surface. 3 plus 2u plus v, comma, 2 minus v, comma, 3 plus 4. Here's an example of a problem. Do we all understand what this symbol means?
Yeah, they both go between 0 and 1.
They both go between 0 and 1 individually, right? So if you see something like that, it's just me saying u is between 0 and 1 and v is between 0 and 1. Okay, tell me how we do it. Yeah, Edward?
Take the partial.
Yeah,
Here we
Edward.
take the partial derivative with respect to u, and then with respect to v.
So r sub u would be what?
It will be negative 2, 0, and 1.
Positive 2.
Oh, positive.
2, 0, 1.
And 1, yeah.
Mm-hmm.
And the bottom will be 1, negative 1, and 0.
And now what?
You could cross product them.
You're going to cross product them. There, you can sort of line them up this way to sort of save yourself writing space. So that's your I, J, K. And so this would mean that your normal vector is going to be given by 0 plus 1, comma, 0 minus 1, but you take a negative of that, comma, minus 2, 0. So that's your normal vector. Now what?
You put it in the, you do the square root thing, the square root thing? Where you
Right, so you need to find the magnitude of the normal. How do we find the magnitude of the vector? Square root.
1 squared plus 1 squared plus 4.
Your square each component, add them together. So that's 1 squared plus 1 squared plus 2 squared. So that's 4, 5, 6. So this is just radical 6. Okay, now what?
In double integral,
So you're going to double integral.
0 to 1. Okay.
0 to 1 on both, because that's how it was described. And it's just radical 6. And in this case, it really doesn't matter if you do du dv or dv du, they will be the same. What's that?
Radical 6.
It's going to be radical 6. Just walk me through the steps.
Radical 6u.
I want to make sure as a concept you guys, because some of you forgot your Calc 3, so just walk me through the steps here. Yeah?
So 6u,
Mm-hmm.
0 to 1.
So you leave this integral out there, right? So you do the inner integral first, so you ignore the v's for a second, Integral of this with respect to u is my radical 6u. Fundamental theorem of calculus, plug in the 1, plug in the 0. So that's going to give you radical 6 from 0 to 1 dv. Same idea happens here, radical 6v between 0 and 1. And so that's going to be radical 6. Question, what kind of surface is this?
2D.
Well, I know it's 2D, it has two parameters.
It would be a rectangle probably. No?
It's a plane.
It's a plane.
So you should be able to look at that and know, oh, that's a plane. So I'm really talking about the plane. Basically, there's a part of a plane hovering over a rectangle, right? It's like 0 to 1. And there's a plane above it here doing this thing. Okay. Not so bad. Okay.
Professor,
Yes.
so would there be any case you have to do dv first and then du, or it does not matter? Do you
It matters in the sense that one might be harder than the other. Here it's just as easy to do one than the other because we're over a rectangle where they are both going to two constants. But in general, remember, the double integral describes the region that you're shading. Right, so if you weren't over a rectangle, you set things up differently. I probably have an example where it's not over a rectangle, so it's a little bit more complicated. I also gave you the limits here. Yeah, so let's just do this one and then I can come back to that question. Surface is given by another one. Okay, that's the example. What kind of surface is that? It's a sphere. So really, I'm just asking you to find the surface area of a sphere. What's the radius of this sphere? So the question is to find the surface area of a sphere of radius 1. Does anyone remember what the formula is for the surface area of a sphere?
4/3 pi r cubed. I mean, no, that's.
It can't be r
sorry.
cubed because it, right?
4 pi r squared?
I don't remember.
4 over
let's just do it. But if you did remember, you could just write down, oh, this is just a sphere of radius 1. Area is given by 4/3 pi, and that's the answer. You could do that. I would accept that answer. But if you're like me and you don't remember what that is, then you're kind of stuck going through the motions here. All right, so let's actually go through the motions. What do we do?
R sub u?
take the derivative. Just to the u.
With respect to u, what would that look like?
So it is a cosine b.
Can we convert these back to x, y, and z?
Huh?
Can we convert these back to x, y, and z before going forward?
Let's just do it directly this way, and then I'll discuss that possibility. Cosine u, cosine v, and
Cosine u, sine b,
cosine u.
minus sine u.
Correct? R sub v.
Minus sine u, sine b. Sine u, cosine b. Zero.
Right? That. given by log out this one, that's 0 plus, this is sine squared u cosine v, comma. Go to the middle, that's 0. Here we have sine squared u sine v. Well, we take the negative of that, so yeah, so that's going to be sine squared u sine v. And block out the last one. So it's this times this, which is what? Cosine squared v sine u cosine u, comma, this one, that's going to be plus sine squared v times cosine u sine u. So the magnitude of the normal,
Professor,
yeah,
the middle one wouldn't be negative sine square u sine v.
Yeah.
that's 0 minus this, but
And
that's,
then, so that is
yeah,
the
but then you
plus.
take the negative of it.
Exactly, so the
No,
negative,
that's right.
No, it's
it is,
Because these two are negatives. So the negative cancel
So-
the negative when I
so-
multiply, and then we
so-
apply another negative.
so 0 minus, then that will be plus, so minus, oh yes.
Okay, magnitude. It's going to be this square plus this square plus this square. Okay, so what is that going to look like? This square is going to be sine fourth u cosine squared v plus sine fourth u sine squared v plus, what's this one going to be? Cosine to the fourth v sine squared u cosine squared u plus 2 times this times that. So that's going to be 2 times, these guys are the same. No, they're not. So that's going to be cosine squared v sine u cosine u times sine squared v cosine u sine v plus sine to the fourth v cosine squared u sine squared u v.
Does it like cancel out to 1 or something?
Well, hopefully something will cancel here. Okay, so what is,
Didn't you have just simplified the last
Yeah, so
coordinate?
it's cosine u.
Because cosine squared v plus sine squared v?
here,
Oh wait, is the last one the sine v? I can't even tell.
yeah, that's,
So it would have been sin u cosine u plus
Yeah.
cosine u sine v.
The different variables.
are these different, these are different?
They're different, right? No.
Sine u and sine v.
Okay.
No, they're the same.
Are they, is it right though, or did I make a mistake?
I think it's not right.
Can we integrate this?
So here,
Sine
so this last component came from me blocking out this.
So
So
cosine,
it's cosine v squared,
It's into 1.
it's sine u cosine u,
Yeah.
that's right. And then this
Yeah,
is
that's right.
sine v squared,
That's sine u at the end.
so this is sine u.
Yeah. Okay, yeah. then
Okay,
just
so
take
now we could have simplified
Yeah.
that, yeah. Okay, so this whole thing, really just is sine u cosine u. right, by applying the fact that cosine squared plus sine squared is 1. You can factor this out and you're left with that times 1. And so we would square that here. That'd be sine squared u cosine squared u. A little bit nicer. Can we simplify anything else here?
Yeah.
What else can we do?
Cosine B and sine B. The same.
Yeah.
Here. So that's just sine to the 4th of u.
Yeah.
I have sine u.
Plus sine squared u cosine squared u. What can we do now?
Take out sine squared.
You can factor out a sine squared. And so it ends up being sine because our u is between 0 and pi and our sine is positive there. Technically it's the absolute value of sine, but it works out to sine here. There's a point to me going through all that, by the way.
Professor, wait. How
Which is
do-
kind of related to Jonathan's question at the beginning. Yeah.
How do you get sine square u from sine to the?
Factor out a common sine squared here.
Okay, so
You'll have sine squared times sine squared u plus cosine squared u, which is 1.
one.
So you
Okay.
just end up with sine squared. Okay. Now there are a couple approaches to this. One, you can realize that if you're parameterizing a sphere using spherical coordinates, this kind of process will literally always kind of happen. You can imagine if there was a row here, a row here, a row here, what would have happened? Where rho is just a constant that represents the radius of the sphere you're talking about, what would happen?
What do you mean, what would happen?
Yeah, pretend there was a row here instead of a 1.
It would just be rho sine u.
Then you would have ended up with rho sine u, right? So that gives us a couple approaches. So one, you can just remember that for a sphere, if I parameterize it with spherical coordinates, my normal, the magnitude of my normal is always going to be that guy. You could go that way, okay? That's one thing you could do. So you can do this once and never want to do it again. And so you just remember, for a sphere with cylindrical coordinates, with spherical coordinates parameterization, the magnitude of my normal is always going to be rho sine u. That's one approach you can take. If you happen to be the kind of person who likes memorizing stuff. I'm not, so I'm not going to want to memorize that, but if that's your thing, you can do that, and that's fine. Okay. If it's in a situation where you don't want the magnitude of the normal, but you actually want the normal, then that's a little more complicated. You'd have to memorize this. But again, if that's your thing, if you have a great memory, that's fine. But anyway, let's actually finish up this problem. So, do we have space to continue? Did you guys copy this so far? Okay. So remember, it's sine u was the magnitude of the normal. So what does that mean for us now?
And then you need to integrate it.
Now we just have to integrate that. Double integral of sine u. So, and again, we can do any order here. So say I put the v on the outside, that's 0 to 2 pi, 0 to pi. And what would I have? So because this thing doesn't have any v's in it, and its limits doesn't have any v's in it, we can sort of apply Clairaut's theorem and sort of even notice that we'd have gotten a multiplication by 2 pi on the outside. To kind of remind you of some shortcuts that you would have learned from Calc 3. And then, what would this turn out to be?
4 pi?
So negative cosine u.
Right, so that's negative cosine u between 0 and pi. Cosine of pi
Negative 1?
Negative 1.
is negative 1, but we take negative negative 1, so that gives us plus 1 minus cosine of 0 is 1, but we take a negative 1 minus a negative 1, so 4 pi. How about another option? Okay. So we want to examine all the options that we could have solved this problem. One, we could have solved the problem exactly how we did it there. Two, you could have it memorized that the magnitude of a normal vector of a sphere is just going to be rho sine u with this parameterization, and you could literally skip the part where you compute the normal and jump to there. Give me another option, another way you could have done this.
So when you just memorize that the rho sine of u would be the magnitude of the normal vector, you integrate to the rho sine of u.
Yes.
What would be the value of the rho? 0 to pi?
The rho is a constant in this case.
Okay.
What's wrong with memorizing that? It's
Huh?
not that. What's wrong with memorizing that? That's not a long thing to memorize.
I never said anything was wrong with memorizing. I literally said, if that's you and you want to memorize it, that's fine. I
Seems
said that.
condescending, like it's wrong.
I mean, so if you
Such
say
an
rho
instigator.
sine of u,
Huh?
if you say rho sine of u integral, so it would be
Yeah.
still.
And by the way, rho has to be a constant here because we know a surface can only have two variables, so you wouldn't think of the rho as a variable anyway.
Okay.
Right. So you could have, you can automatically know that to find the surface area of a sphere, you do that.
And then you would still get 4 pi or 4 rho pi.
Rho would represent the radius of the sphere.
Oh,
So if the radius was something other than 1, it would
One.
just be that times this.
Okay.
Okay. Give me another option of how we could have looked at this.
It'd be X, Y, and Z.
Yeah, so let's say you look at this, you recognize, hey, that's just really a sphere. In fact, that's the unit sphere. What could you use, how could that be an advantage to you?
X squared plus y squared plus z.
Right, you could just realize that this guy is just really x squared plus y squared plus z squared equals 1.
1.
Okay? What could you have done then?
Find the normal vector by the formula.
Sure, and what would that be?
It would be negative 2x. No. You have to go z equal to square root
1 minus x
1
squared
minus
minus
x
y squared
and then
square
the square
root.
root.
Technically, I have a plus or minus here, but that wouldn't bother me so much. Why?
You could just do double the area of one of them.
Because I just double the area of one of them, because I recognize that, hey, this is a sphere. The area of the top is going to be the same as the area of the bottom.
Bottom.
So I'd really just double
The
the integral for,
positive one. So
right, so I know my normal is going to end up to be minus fx, minus fy, positive 1. The magnitude of that is going to be this squared plus that squared plus 1 dA, right? Over that, right? So that's another option you could have done. Which is something, these are things you want to explore, especially now if we're like 2 weeks out from the test, right? You don't really want to be, oh, let's see all the ways I can do this, like 2 days before the test. You don't want to do that. But like, you're 2 weeks away from the test, you can take this week, whenever you're going over the homework problem, sort of think, what other way could I do this? What another way to look at this? Sort of explore different options. Now's the time to explore. And then you kind of get into a groove and you kind of realize, okay, this is what would be easier for me. I prefer to just memorize this thing for this particular shape and run with it. Or, oh, I prefer to, whether I recognize this, to change it to scalar form and run with that. Or, oh, I just do the direct computation because I know I'm going to mess up somewhere because you've been practicing problems. So a part of studying is actually learning how you learn and the best way for you to do it. Personally, I don't like memorizing, but there's nothing wrong with just memorizing that the magnitude of a normal for a sphere is always going to be rho sine u. I'm not going to knock that if you want to do it, but it's just, it wasn't something that worked personally for me. Personally for me, I would have preferred to do this. But any of these 3 ways that we discussed to do this one problem is fine. Yeah.
What is that before the double integral is 2 or 3?
Come again?
2. Oh, the number before the double integral.
2 is
This is a 2.
Okay.
Because the idea is I'm only concerning myself with the top because I know it's a sphere, so the bottom will give me the same answer.
Okay.
So I just use the normal vector from the top, which is this, find that magnitude, integrate it, but I know I have to double the answer to account for the bottom.
Does all this method also apply to ellipse? Ellipsoid?
Yeah, ellipsoid would be the same. The difference between a sphere and an ellipsoid would be that the coefficients would be different.
Okay,
So for a sphere, you'll always have the same coefficients. So if there's a 1 here, there has to be a 1 here, there has to be a 1 here. If there's like a 1 here and a 2 here, it's now an ellipsoid. The constant number in front of these terms would be different.
So can you still use the rho sine u?
No, that would change things a little bit. So if you want to go with that, you're going to have to memorize. For a sphere and for an ellipsoid, it would look like this, and for this, it would look like that. It's just a snowball. Like if you go the memorizing route, which is why I don't like it, because I don't really have a particularly good memory. But I sort of realize that if I take that approach here, it's going to cascade in me having to memorize a bunch of things, and I don't like memorizing.
But this
So.
work. But this method will work.
But this would work.
Okay.
And it's not really something you have to memorize. It's just something that if you know the concept, you could figure that out. So I won't have to worry about what was that again? And if you're in a test and you're freaking out and you're anxious and you start forgetting stuff, like for me that's not going to happen. But for someone who might memorize, it depends on the person.
Wait.
Yeah.
In that second method,
Yeah.
where does the pi come in? Because we still have to end up with 4 pi, right?
The pi would come in because your region of projection is a circle, which you would. The best way to do it would be to switch to cylindrical coordinates and do the r and the theta, and that's where the pi would come in.
Okay.
So it would be like 0 to 2 pi, 0 to 1, and this would be the r dr d theta. And that's where the pi is going to come in, because your region of projection.
Professor,
Yes.
for cylindrical coordinate, wouldn't it be r dz dr d theta?
Why wouldn't it be r dz dr d theta?
That was the formula in the book.
We're doing a double
Sure,
integral.
but I'm asking you guys, why would you know not to set it up dz dr d theta to answer his question?
We're doing a double integral, not a triple
Oh,
integral.
A double
that's-
integral, not a triple integral,
Oh,
is the question to that.
Is that
Cylindrical in
okay. Okay, that was
cylindrical, if you're doing a triple integral,
yeah.
there's an r dz dr d theta. That's because there are 3 variables you're working with, which means you have to have a triple integral. You wouldn't do a setup like that with a double integral. So this is why I talk about those concepts in the beginning, you know, like that thing. I'm not just doing that to mess with you guys. Like, knowing that a surface only has 2 variables and that it relates to a double integral, these are the basic little things that can clear up a lot of confusion. So you'll know that the setup here, you'll never have to worry about a z, because you know that there are only 2 variables, it has to be a double integral, and that you kind of never have to worry about things like that creeping in. Right? So basic things like that, when you look at all your equations for surfaces, you also need to look at things like that. How many variables am I dealing with? Is there ever a triple integral, and things like that. Right? So it's one of the telltale signs of knowing sort of how much a student understands. So it's like if I'm grading the test 1 and ask for the equation of a line and the student gives me the equation of a plane, I'm just like, whatever, this person doesn't know anything that's going on. Other telltale signs are things like, if I ask you to compute an area and you write down a triple integral, I'll know you have no idea what's going on, right? If I ask you to compute a volume and you put a triple integral, then yeah, okay. Right, but these are just basic things that you should be aware of. Okay. Let's actually move on to the next section. That's all I want to do for this section. So being able to find areas with respect to parameterization is important. You just use the magnitude of RU cross RV, or you can use the other formula for normal vectors. But perhaps even more important than that, the thing that you want to take away from this section is how to find a normal vector. You're going to want to be able to do that very quickly in general.
Professor, didn't you want to do a problem where you need to set up dv first and du first to make it easier? Like, do you have a problem like this?
No, I didn't do that here. That's more of a Cal 3 topic. It's more like if they told you about a region of projection. Let's say you know that this is in the xy plane.
Okay.
Right, so really something's happened in 3 space and you have a surface and it's projected into the xy plane. Let's say, suppose you know it projects like this, where the y goes into 1 minus x squared, and it cuts off here, so you have that. Like, how would you set that up in terms of the limits on the integral?
So this one you will set up dy first, and then the dx.
It doesn't matter, you can choose. So tell me what you choose and how you would do it.
X, Y is given in 0. Wait, no. Y is given
No,
Y goes from 0 to 1 minus x
0
squared.
to 1 minus x squared, and then x goes to 1 to negative 1.
Okay, now what does that mean? Now when you're setting up the double integral, blah, 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 what does that mean you're setting it up as?
You would set up as dy dx, since
Okay,
dx
and
is
so now the y, that would be here, and this would be here. Because the inner integral has curves, the outer integral has constants. So who you choose to be the curves and who you choose to be the constant directly affect how you set up the integral. And you also should remember that in a triple integral, the inner integral is surfaces. So the surfaces that you're bounding go on the inner integral. The outer integral is curves for the projection region. The super outer integral is going to be the constants for the projected region. In general, the two outer integrals talk about your projected region, whereas the inner integral will talk about the surfaces that are hovering in space. So that's sort of a Calc 3 idea. It's not really the main thing I wanted to do, so I just gave you the links to make it easier. Didn't want to spend too much time on that. But yeah, all this, if you don't remember this, remember the 3 sections that I mentioned in this 12.5 through 12.7, you'll go through problems like that. That's it for now. Let's get to the last topic. So we're not going to finish this for sure, but we'll probably finish this up on Tuesday, and that will be all you need to know for the next test. So we're going to talk about surface integrals. There are 2 kinds. We're going to introduce both of them. So it's like the higher dimensional analog of a line integral. So let me just give you the definition here, then we sort of talk about it. So S is a surface. You could perhaps have a parameterization. I'll tell you the limits here. And the surface integral we need another function. Define this one. RFUV, let f of xy be a smooth surface. Meaning we can find all the partial derivatives and they're all continuous and things like that. Then the surface integral over f with respect to s is given by this is the notation, and I'm going to give you the definition as well. The double integral over s f of xy s equals double integral over d of f of, you plug in your parameterization, multiplied by the magnitude of the normal vector, dA.
Professor,
Yes.
what is this? Then the surface integral over f and w1, r1, t1 you said?
With respect to.
Oh.
So that's the equation. You can notice that here we're multiplying by the magnitude of the normal because, let me just emphasize something here. There are two types of surface integrals. There are surface integrals over scalar fields and surface integrals over vector fields, so let me make a note here. This is called a surface integral. Over the scalar field. Emphasis on the scalar field. We're going to talk about surface integrals over vector fields pretty soon. That comes at, I'm pretty sure, at the end of this chapter.
The magnitude has to be 2 lines.
No. As long as you know what the magnitude of a vector means, that's fine.
Jhevon?
Yes.
So if before we were finding the area of the surface, what is a surface integral really finding?
I'm going to mention that. Just want to make sure everything's okay here. I think you can have a third variable here. Because we're often going to think of this happening in 3 space. So it's a 2-dimensional surface, but we're looking at it in 3 space. Let's continue. So here, to answer your question, let us compare to something like the integral along C of f ds. All right, so we're going to look at this guy, the line integral along f ds. This is a line integral. Versus the double integral of f d big S. This is called a surface integral over a scalar field. So again, we can imagine something happening in 3 space here, something happening in 3 space here. So here there's a single integral, which means there's a curve that we care about. So there's a curve living in perhaps the xy plane, doing its thing here. And what this does is for each point xy on this curve, it plugs out an output f, which gives you the height of that curve. And so you're really finding the area of this fence given by, at every point, is given by the height of f. Right? And so this guy gives you the area of the fence. That's a geometrical interpretation. We never actually use that interpretation. We use this to compute other things, but that's geometrically what we're computing. For this guy, what are we computing geometrically when we find a surface integral? It's probably good to look at this versus the Calc 3 version. If you have a double integral over d of some function dA. Let's talk about this first. What does that actually mean? How did we interpret this back in Calc 3?
Volume?
It's the volume volume of what? Is the volume below this surface, right? So we had a surface that was given by this equation F. It was projected down to some region D. And if we wanted to find the volume below F that's above the region D, that was your integral. So what happens here is that, remember for the line integral, this generalized the single integral from Calc 1 because on the single integral we were stuck on the axis. We could only integrate over intervals along the axis. We wanted to generalize that to be able to integrate over any arbitrary curve in the plane, right? Similarly here, back in Calc 2, we could only integrate over regions that are in the planes, either the xy plane or the xyz plane or the xz plane. Now we want to generalize that to be able to integrate over any surface. So there's a surface hovering in space, which I would describe as S. There's another function that I want to integrate, that's my F, and I'm projecting that onto that surface, right? So now I'm integrating over something that's some arbitrary surface hovering in space, as opposed to directly projecting it down to the xy plane. Yeah.
So if S is larger than F, then we'll have the entire F area, but if S is smaller than F, we'll only have part of F?
That
Like
would
a
never
shadow?
be the
Like,
case.
is it
Our
casting a
limits.
shadow?
Huh?
Is it casting a shadow on
It's
the-
casting a shadow, yeah. And the limits of the integral will only cover that shadow no matter what. So this, where one is going to, where the space that one takes up is bigger than the other is not a situation we'd end up with. But that's the idea, right? So with the line integral, we wanted to escape being bounded to the axis. Similarly, with the surface integral, we want to escape being bounded to the xy plane. I want to be able to integrate on top of any random surface hovering anywhere. So this integral finds the volume of this object, whereas back in Calc 3, I could only find the volume of an object that's perpendicularly projected down to the plane. And so that's sort of the idea. I want to get away from the fact that I have to project perpendicularly. What if I want to project over here on top of that? That's the idea. Right? You really want to generalize what the integral can do. And so that's what a surface integral gives us. So this pretty much gives us the volume as projected on an arbitrary surface. And really we're assuming the conditions are nice. We can find partial derivatives and we know how to perform calculus on these surfaces. But that's basically the idea. It's never an idea we're actually going to use, but geometrically that's what we're computing. We're going to be interpreting this integral in other ways. Just that there are some line integrals we can interpret as work. We're going to find interpretations for this integral. So we're not always going to think of the geometrical picture. So pretty much what you do want to take away from this is the definition itself, how to actually set up and compute that. Which notice that it involves the magnitude of a normal vector, which means if I ask you to compute a surface integral over a scalar field, you first have to find the normal vector, but your job is not going to be done. You're going to have to take that, put it into a double integral, and compute the double integral, which is kind of why you should be really quick at finding normal vectors. You don't want to spend forever setting up the integral that you have to compute, right? So if you know how to find a normal vector quickly, computing this shouldn't be too much of a problem. You find a normal vector, you plug into the formula, the rest is Calc 3. Okay. Do we have time for an example? I have two examples here. We probably can get through one of them. And then next time I introduce surface integrals over vector fields. Another thing you can note here again, there's a parameterization flavor and a scalar flavor. So if S is given by a scalar,
Professor,
yes,
what is NB?
note.
What the B stand for?
You down.
That's what I've been saying all this time. That's what you want to ask a question about. Like, you're totally minding your own business the whole time. What is the B? That's what makes you perk up your head.
NT, no test.
Huh?
Right.
Nota bene. It's actually an abbreviation of a French phrase that means note. So the B is for the French, the second word in French.
Oh, really?
Anyway, yeah. So suppose we're not given a parameterization, but the surface is described to you in a scalar field. Then all that means is that the formula can be interpreted as this way. You're just going to parameterize this, which is just going to be the x, y, and you're going to plug in the f of x, y. Probably I should have used another variable here. And then the magnitude of the normal we know is going to be partial with respect to x squared plus partial with respect to y squared. Right, that's because, you know, in this case, your n is going to be minus fx minus fy. We can also note here, which would be a nice thing to know. Tell you something that you don't have to worry about. Orientation of n does not matter. So whether you give me the vector that's pointing up or down, I don't care, because what I care about is the magnitude of that vector. I don't care what direction it's pointing in particular. When we do surface integrals over vector fields, the direction that your normal vector is pointing is going to be important. So at this point, it's another opportunity for me to remind you. You probably want to, again, review sketching surfaces so that you can sketch a 3D object. So review 10.6 from your Calc 3 notes, because it's going to make your life a lot easier. Because pretty soon we're going to think of these normal vectors as living on top of an object. And if you know what the object looks like, it's going to be easy for you to visualize what direction the normals are pointing in. So surface integrals over scalar fields, you have the definition. Know that orientation does not matter. Let's do an example. Evaluate double integral over s of x plus 2y ds, where s is the portion of 2x plus y plus 2z equals 6 in the first object. Okay, go. Normal vector, right? Do this, one of the first things you want to do is find the normal vector. Let's find our normal vector. How do I find the normal vector?
You just take the vector, 2, 1, 2.
No, you get the wrong answer doing it that way.
You're gonna do the partials of both and then do the corresponding?
Partials of what? Parcels of what?
The parameterized curve.
Don't we first need to set it as z equals stuff? Like we need to rearrange?
Right as z equals 3 minus x minus a half y. So that would mean, what would our n be here?
It would be negative 1.
No, it would be a positive one.
Partial with respect to x, take the negative of that. It doesn't matter whether you choose a positive, just know what formula you're using. Let's say I want to use this formula. The signs don't even really matter here because we're going to be squaring everyone. So that would be 1. What would this be?
1/2.
A half and 1. So that's the vector I want to take. Notice that the normal vector, there are an infinite number of normal vectors to this plane. 2, 1, 2, 6, 3, 6. There are tons of them. But the magnitude is important to this formula. You're going to want the right magnitude. So you need to choose the magnitude that would fit in with the formula that we had before. So you need to make sure that your normal vector has a 1 in the z component.
Professor, is that a 6 or 0?
6.
Oh, I thought it was 0.
Yes.
Do you set it equal to z because in the integrand it's in terms of x and y? So you,
Oh, arbitrary.
oh, so you can set it in terms of x or y.
Do you know why it's arbitrary? And I'm just keep talking. Let's just jump. Let's finish this. We'll talk about. Remind me to answer the question why I could have solved for anyone I felt like. So next, now what?
Find the magnitude of that.
Find the magnitude of n. So that would be
Radical 2 1/4.
1 plus a quarter plus 1. So that would be what?
1.5?
Huh?
1.5? I mean, if you take the radical of 1.5.
9 over 4
It would be 9 over 4.
plus 3 half.
0, 2. Oh, that's going to be 1.5. Okay, so now what? So we found the magnitude of the normal. So now we're going to jump directly into that formula. We know the double integral over s is going to be equal to
Do we need to parameterize the surface?
it's already no.
So
Well,
would
assuming this formula means I'm thinking of the parameterization as x, y, and f of x, y. Right, that's implied, which means x and y are themselves. I don't have a z, so I don't even have to worry about this. So I'm literally integrating that expression times 3 over 2. Now let's talk about the limits. How are you seeing that? Tell me how you figure that out.
Tried to find the points on the axes where the planes are intersected.
Okay.
And then
So you think of a picture here, because we know that's a plane. How would I draw that picture?
I'd solve for 0 and 0 in each.
You plug in 2 equals 0 at a time, solve for the other guy. So on your x you'd have 3. On your y you'd have 6. On your z you'd have 3. So you know this is the picture. I chose to project into the xy plane because I solved for z. But I could have chosen to project into that triangle on the xz plane or that triangle. You just need to be aware of what you're doing. Okay, so assuming I projected there, that means in the xy plane, my curve looks like this. It's a straight line. So now the question is, how do I set up an integral over that region? And now you come in. So you said?
I said z equals to 0 for the function. I got my line as y equals 6 minus 2x.
So here, we know that this is in the xy plane, which means my z is going to be 0, so I can solve for the y. Y equals 6 minus 2x. So that's y equals 6 minus 2x.
So then your bounds for y are 0 to 6 minus 2x.
So y goes from this function up to that function. That's 0 up to 6 minus 2x, which means I'm doing dy first. Then I do dx, and I can set this up. This would just be 0 to 3. We're out of time. You do all that, I mean, the setup is the hardest part. Assuming you got that far. You would do all that, the answer you should get is, I wrote it down, 135 over 2. Are we seeing why Calc 3 is important?
Yes.
So you have to find a normal vector. You should be able to get through that quickly because you're going to have a lot of trouble. Then you're going to have to figure out what is the object I'm looking at. Where am I projecting? Because that's going to tell you how to set up the limits on your doublet. Again, Calc 3. And then the rest of this is just Calc.
I don't understand why, since there's multiple,
Yeah. Oh, another thing you learn in Calc 3 is that there are literally 6 ways to set up any doublet.
right.
So if I could have chosen to solve for the y instead, then it would project into this triangle. Then I would set this equals 0, solve for that guy, and that would change my limits here, and that would be dx dz or something. Right, there would be 6 permutations.
Professor,
So
do you
it's sort of
need,
a preference.
do you need to know your calculus 3 stuff on after test 2, like those materials cover calculus 3 stuff also? The
The
matrices?
first 3 tests covers it.
Oh, okay.
Because on the third test will include the divergence theorem and Stokes theorem, which you need Calc 3 for.
Oh, okay.